Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. Today we are going to be talking about carbon heteroatom coupling with regard to our overall discussion on CC bond forming reactions that we had done in the last few lectures. Now, one of the main advantages of this organometallic catalyst mediated carbon-carbon or carbon heteroatom bond forming reaction is the fact that these catalysts have achieved this reaction proceed under very mild conditions. So, this in a nutshell is the main achievement of organometallic catalyst. So, what this catalyst has achieved is in reduction of stringent conditions in which these reaction occur in absence of this catalyst. So, this can be seen as a main advantage of using organometallic catalyst is that they are able to carry out all these reactions that would form various types of carbon-carbon bond or carbon heteroatom bond and this bond would be formed under mild conditions which are easily accessible. So, this in my opinion is the main reason why all of these palladium based organometallic catalyst or nickel based organometallic catalyst that we have been talking about for CC cross coupling reaction or that we would be talking now about C heteroatom coupling reactions, they have become very popular for. Now, to go in a bit more details, these reactions particularly with respect to C carbon heteroatom coupling reactions, they can be formed by two different ways. One is nucleophilic aromatic substitution reactions which require drastic conditions, or otherwise they can also be formed by addition of alkene or alkyne, which also is a very challenging reaction to perform in absence of these organometallic catalysis. So, with that being said, what we see or what we would see is that all of these types of reaction would become very favorable when influenced by this organometallic catalysis. So, with this let me start my topic today, which is about carbon heteroatom coupling reaction. The two classical ways or two approaches that for making carbon heteroatom bonds are one through nucleophilic substitution reaction, aromatic substitution, which requires drastic conditions, and the other approach obviously involves addition to unsaturated compounds like alkenes and alkynes which also is challenging in absence of catalyst. Now, the reason for addition reaction being challenging in absence of catalyst, because both the nucleophile that is being added as well as the alkene or alkyne, both are considered to be electron rich entities, and so they are mutually averse to be reacting with each other, and hence these addition reactions to alkynes and alkenes are in fact very challenging in absence of this catalyst. So, what we see over here, the ground already made for the acceptance of these transition metal catalyzed carbon heteroatom coupling, as such coupling would find a way around this type of existing methods, which are nucleophilic aromatic substitution reaction that require drastic condition, or these addition reactions to alkenes and alkynes, which in absence of catalyst are very challenging. So, these new found transition metal mediated reactions, coupling reactions would find way around to perform the same reactions under very mild conditions in an effective manner. And in this context, what we are going to be discussing a number of reactions which have which would be catalyzed by organometallic catalyst, and among these are amination of arenes, hydroamination reaction, hydroboration, and hydrosilylation reaction. And in these the first one would be CN bond formation. Hydroamination would also give CN bond formation, hydroboration would give CB bond formation, and hydrosilylation as the name suggests would give CSI bond formation. So, these are some of the reactions which we are going to be taking up that would show that how these transition metal based organometallic catalysts help perform these reactions, which otherwise in absence of catalyst would be extremely difficult to do so. So, having said that, we are going to focus on carbon heteroatom coupling, particularly on amination of arenes. Amination of arenes. These reaction was recently developed by recent, I mean about 2 decades back, by Professor Buchwald at MIT and Professor Hartwig at Yale University, who developed this reaction as recent as 1998 for this amination of arene. So, Buchwald 1998 and Hartwig 1998 recently developed the palladium catalyzed amination of arenes. and we are going to be discussing the catalytic cycle in bit more detail, but what is important to know is the reductive elimination step leads to the formation of this carbon heteroatom coupled product. The reductive elimination step offers the carbon heteroatom coupled product, and this is sort of explained by this equation over here, where it is AR M 2 X R N. X can be a heteroatom oxygen sulfur, then N equals 1. X can also be a nitrogen when N equals 2. So, that will reductively eliminate to give M 0, and this carbon heteroatom cross coupled product AR X R N. So, what we see is that this reductive elimination which leading to the formation of carbon heteroatom coupled product or formation of the carbon heteroatom bond, similar to what we had observed for various cross coupling reaction, where too we saw carbon carbon bond was indeed formed in the reductive elimination step. So, this is sort of a similar translation of the chemistry that we see in carbon heteroatom bond formation to what we had observed for carbon carbon bond formation. That is, the reductive elimination step indeed leads to the formation of carbon heteroatom bond, similar to what was observed in the cross coupling chemistry that we had discussed in our earlier classes. So, with that said, let me just briefly elaborate the catalytic cycle for this amination of arene reaction, so that we can compare the catalytic cycle with that we had discussed for carbon carbon bond forming catalytic cycles earlier on in our lectures. So, the reaction starts with the palladium 0 species L2 PD. So, that adds aryl bromide. Now, this step is similar to the oxidative addition step. To give the product Ln PD Br Ar. Now, in this case, immediately after oxidative addition, coordination of amine to palladium occur. Now, this is sort of different than what we had observed in CC cross coupling reaction, where it was a transmetallation reaction, but in this case where we see coordination of amine occurring onto the palladium, and this is illustrated by in the scheme as shown over here. H N CH2 R1 R2. So, this amine comes and coordinates to palladium, giving L PD Br, Ar, NH, CH2, R1, R2. So, after the amine is coordinated, so this is the coordination of the amine. The next comes a base initiated deprotonation, which occurs using the base sodium butoxide giving sodium bromide plus T-butanol. So, sodium bromide comes off and this proton protonates the butoxide giving T-butanol, resulting in the formation of this Ln PDAR and CH2 R1 R2. So, this step is now the deprotonation step, amine deprotonation step, and the deprotonation of amine results in formation of a amido functionality. So, this is a neutral amine which is cationic after its lone pair gets coordinated to the palladium, becomes an amido functionality after deprotonation with sodium T-peroxide giving sodium bromide and butanol, which will undergo reductive elimination to give the desired product AR N CH2 R1 R2, and this step is called reductive elimination. This step is called the reductive elimination, and this is how the catalytic cycle proceeds. So, if one were to compare this catalytic amination of arene catalytic cycle with that of say Suzuki catalytic cycle, one would also see that here too there are 4 elementary steps, and 2 of which are common, similar to what was observed for Suzuki, that means the oxidative addition and the reductive elimination. However, the other 2 elementary steps, the amine coordination and amine deprotonation, are different from what was observed for the palladium mediated cross coupling reaction, in which it was transmetallation and trans cis isomerization reaction. So, what we see is the fact that we had stated earlier as well, that carbon heteroatom bond is indeed formed during the reductive elimination step. There is a competing decomposition pathway that may also occur, and that is this if there is a beta hydrogen on the nitrogen, there is this beta hydride elimination pathway marked in the blue, giving imine and corresponding palladium hydride complex which this is a beta hydride elimination pathway of which gives the imine along with the palladium hydride aryl hydride complex, which eventually undergoes reductive elimination to give aryl hydride, and with the generation of the palladium 0 L2PD species. So, this is reductive elimination. So, what we see is that in addition to the catalytic cycle involving amination of arene, if the amine has a beta hydrogen, a secondary pathway may be possible in which a generation of imine would be accompanied through a beta hydride elimination pathway alongside the formation of LNPD aryl hydride complex that eventually again would reductively eliminate to give arene and the palladium 0 species which can then again participate. So, what we see is that the decomposition pathway would churn out two different products, one is imine and arene, and that the presence of these two compounds, the imine and the arene, would definitely indicate the existence of the decomposition pathway as shown in blue. Otherwise, the main pathway which would lead to the elimination of arene is shown in black as usual. Now, as has been discussed in details, that this reaction is has a large scope of broad scope of utility. Aryl amination has a broad scope of utility. One, it is good functional group tolerance. And preferably electron rich amines and electron poor arenes favor the coupling. And electron poor arenes favor the coupling. So, electron rich amines means the nucleophile is extremely nucleophilic, and electron poor arenes means the electrophile is extremely electrophilic. So, significantly nucleophilic reagent would definitely react faster with significantly electrophilic substrates, and that is quite intuitive, and that is spelled out in the lines over here that says the electron rich amine and electron poor arenes favor the coupling. The coupling of primary amines with arenes require chelating ligand. require chelating ligands, and retention of configuration is observed in the alpha position for intermolecular coupling. In terms of asymmetric reaction, at C alpha for intermolecular coupling when catalyst has binap or DPFF, whereas also retention of configuration at C alpha in intramolecular coupling when catalyst has monodentate ligand. So, with this I would like to conclude today's discussion on amination of arenes, and today in as a part of the carbon heteroatom coupling, what we talked about is this amination of arenes, which was developed by Buchwald Hartwig as late as 1998, and which uses palladium in carrying out this amination of arenes under mild condition. When looked, and what we discussed is the fact that this carbon nitrogen bond formation in annihilation of amine it took place during the reactive elimination step, and we have also looked at the catalytic cycle for this amination of arene, and what we had observed that this catalytic cycle contains a 4 elementary step that involves oxidative addition, amine coordination, amine deprotonation, followed by reductive elimination. And when we compared this catalytic cycle with that of the palladium mediated cross coupling reaction, what we had seen is that 2 of the 4 elementary steps are common with that of the palladium mediated cross coupling reaction, and these 2 steps were oxidative addition and reductive elimination. However, in amination of arenes, there are 2 steps which are different than what was observed for palladium mediated cross coupling reaction, and these 2 steps were amine coordination and amine deprotonation, leading to the formation of a palladium imido species. Now, we have also looked at the decomposition pathway that may be existent if there is a alpha hydrogen on the amine, and what we had seen that there is a beta hydride elimination pathway is possible if there is a presence of alpha hydrogen in the amine, and that pathway leads to the formation of imine along with the palladium aryl hydride species, which undergoes reactive elimination to give arenes along with the formation of palladium 0 species. Now, one thing which has made this aryl amination is its broad scope of utility, its good functional group tolerance, and what has been observed that electron rich amines which are extremely nucleophilic favors coupling with electron poor arenes which are more electrophilic, and the coupling of primary amines with arene require chelating ligands. Also, it has been observed the retention in the asymmetric form, the retention of configuration at alpha in intermolecular coupling requires chelating ligands, whereas retention of configuration at alpha intramolecular coupling require monodentate phosphine ligands. So, with these I am going to conclude today's discussion on amination of arenes, and we are going to be discussing a bit more on the various applicability that have been reported for amination of arene in the next class, and then take up another important example of a CN bond formation, particularly from the perspectives of hydroamination reaction. I once again thank you for patiently being with me in this lecture, and I look forward to covering this topic of amination of aryl in bit more detail in the next lecture, and then take up this new topic of hydroamination in the next lecture. Till then, goodbye and thank you.